right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at factors affecting rate. Now, this is the second part, and if this is the first year you're with me, part number one's not even done yet. If this is not the first year at Wiley High School, you've already watched part one, and here we are at part two. Today we're going to talk about Arrhenius' equation and how we can relate this activation energy and temperature and how they affect those rates of a reaction. Now, this is all kind of based in the collision model, and so there's three things that the collision model states. Number one, and you want to get these down, is that molecules actually have to collide in order to react, right? And we've been saying that for a while now. The other part of collision model, and the second part says that when these molecules do collide, that they have to be properly oriented in order for a successful reaction to occur. And then the third part, and this is the one that we're really going to be focused on today, is that when these molecules collide with proper orientation, that they have to have enough energy to overcome the energy of activation barrier. All right, so those are my three things. They have to collide to react, they have to have proper orientation, and they have to have enough energy to overcome the energy of activation barrier. All right, and so we're just going to generally sketch, and I didn't write those, but I want you to write them. We're generally going to sketch out a potential energy diagram for a reaction. The reaction that I'm going to be interested in is over here. I'll write it. So we've got 2NO plus Br2. Now, I know that's kind of sloppy. And so let's go ahead and rewrite it over here. I got 2BrNO, and so that's my reactants, and then my products here. Because what I want to do is on this potential energy diagram, I actually want to start talking about when I do get to the top of this peak here, right? I've got proper energy, I've got a collision that has occurred, and it's a successful collision. What we end up with at the top of this is what we call the transition state, or an activated complex. You can see it referred to as either way. So it's either called a transition state or an activated complex. And what happens is I end up with kind of a hybrid molecule, if you will. Finish drawing this up here. And all the bonds are still there, but some of the product bonds are also being formed. And so I've got this highly unstable activated complex, and then my reaction can either proceed forward or it can actually go backwards at this point, depending on, I guess, just whatever it feels like, if you will. But we've got to have enough energy of activation to overcome that energy of activation barrier. And what I'm talking about is this area here. But once I get to the top of that, I've actually got, and again, we've seen this before, and I just wanted to introduce it to you, is that activated state, or the transition state, or the activated complex, all right? And so this is what we're actually going to be looking at today, and what we're going to be focused on is how do we get, and how do we define how my molecules get up this hump and get over that energy of activation barrier, all right? Okay, and so now what we want to do is we want to take a look at how does this temperature actually affect that energy of activation. Well, what do we know? What are a couple of things that we do know? Well, the first is we know that a taller, if you will, quote unquote, energy of activation means I have a slower reaction. I have less molecules that can actually make that climb, and so since I have a slower reaction, I have a smaller value of my rate constant. And so let me finish that. All right, and then the next thing is that we understand that reaction rates increase with an increase in temp, right? And we've seen that explained by Boltzmann's distribution, but we want to see, and what we understand is that that relationship is not linear, right? And that generally a 10 degrees Celsius increase in temperature is going to actually double our reaction rate. And so we want to get that down as well. We understand that reaction rates increase when increase in temperature, and we need to understand the relationship is not linear. We're actually going to define that mathematically today, and you'll understand why it's not linear. It's actually an exponential relationship there. And so what we want to do is we want to track all the way back to Boltzmann, and we want to take a look at his distribution. Well, I'm just going to draw two different temperatures here. I got T1, and then let's make a T2 in yellow. And so you'll see, if we're looking at this, we understand that temperature number 1 is actually our lower temperature, right? Remember with Boltzmann, our curves flatten out as we increase our temperature, and the number of molecules that are above this energy of activation barrier, right, increases. Now notice this isn't just a simple doubling. If I double temperature here, increase temperature, right? It's not a linear relationship. I push these molecules across that activation energy barrier. And so we want to know, how do we describe that relationship between that energy of activation barrier and how many molecules are on the other side of it? And most importantly, how do we actually quantify this? Okay, and so the Arrhenius equation is actually what we're going to do, and we'll take a look at it. It's going to relate Boltzmann. Boltzmann is a qualitative, if you will, a qualitative description about why the temperature increase affects that rate of reaction. But we want to be able to quantify this, and this is tricky because at this point in time in 2015, you don't actually have to quantify this. You're not going to have to solve anything with the Arrhenius equation. It's just another way to describe this relationship between the energy of activation barrier and the temperature, right? And so Arrhenius equation is my rate constant is equal to what we call a pre-exponential factor. I'll explain that in just a second. And then we've got the natural log there, energy of activation divided by RT. And so this, the energy of activation divided by our gas constant and temperature, we have to understand how these values actually affect, because this is what we're trying to get to, is what are these value relationships? What happens when activation energy goes up versus what happens decay and vice versa? And so to do this, I just played with the calculator and I took some E values. I took e to the 20, e to the 5th, e to the negative 5th, and e to the negative 20th. And so e to the 20th is equal to 4e8. E to the 5th is 148. E negative 5 is 6e negative 3. And e negative, that's negative 20, is 2e negative 9. And so what we want to see is just the general relationship is that the more negative my e value exponent becomes, the smaller my rate constant will be. All right? And so that's really important, is that the bigger this value gets, because of this negative value here in front of my energy of activation, the bigger that exponent gets, the smaller the value of K and the slower my reaction is. And so we have to understand that a large energy of activation, actually this mathematically explains why that rate is so slow, because K is going to be small in that particular case. Now my pre-exponential factor, that's what this A value is. This represents, and this is where it relates to Boltzmann's distribution, this represents the fraction of molecules that have enough kinetic energy to actually cause a reaction when they do collide. All right? And so this is going to be a table value. This is something that we can look up and we can plug into this. And it does affect that rate. And this is why Boltzmann's distribution can also describe how these temperature changes affect qualitatively the rate of my reaction, because they're defined here in my pre-exponential factor, and we have to see that the bigger this gets, the bigger my K value becomes, and that's why we can also use Boltzmann's distribution to actually define effects on rate as well. All right? And it's just really important just to know what we're looking at here, right? And then the other part of this that we're going to relate temperature to is, again, the higher the temperature becomes, right, the smaller that overall exponent becomes, and the smaller the exponent, the larger the value of K, right? And so again, it's understanding these relationships over here, that bigger exponents mean smaller K, smaller exponents in this particular case mean a bigger rate constant value, and the larger the rate constant, the faster my reaction is going to occur. All right? Okay, that's it. This was the coup de grace of that particular lecture. We just needed to get Arrhenius' equation down. We needed to make that relationship between Boltzmann and mathematically defining how that rate constant is affected by temperature. If you have any questions, get them down. I'll see you in tutorials for those. Otherwise, I will see you in class.